Let's take a look at some examples here where we get to directly apply the probability of a sequence of events. So this first one says a coin is flipped and a die is rolled. Let's find the probability of getting heads on the coin and a 4 on the die. So the probability of heads and a 4 on the die, or I'm going to say the probability of heads on the coin and then a 4 on the die, is going to equal the probability of heads multiplied by the probability of a 4 on the die. And notice the way that I've written this reflects the fact that getting a 4 on the die is completely independent of getting heads on the coin. The probability of getting heads on the coin is 1/2, and the probability of getting a 4 on the die is 1/6. So we end up with an overall probability of 1/12. If you take 1/2 and you multiply it by 1/6, you get 1/12. And 1/12 in decimal form is equal to 0.083. 0.0833 if you're going to 4 decimal places. So a little over 8% chance of getting heads on the coin and a 4 on the die. Okay, let's look at example B. As part of a psychology experiment on perception and memory, colored balls are picked from an urn. The urn has 3 red balls, 2 green, and 5 white balls. And so I'm going to denote this with 3 R's, 2 G's, and 5 W's. When a ball is selected, it is replaced. And so remember, when balls in a situation like this are replaced, then that means that the second event that occurs is completely independent of the first event because of that with replacement idea. So let's find the probability of selecting a green ball and then a white ball. So the probability of going green and then white would be equal to the probability of a green ball multiplied by the probability of getting a white ball. And this is equal to, the probability of a green ball is going to be 2 out of 10 multiplied by the probability of a white ball, which is 5 out of 10. And if you multiply your numerators, you get 10. You multiply your denominators, you get 100. 10 divided by 100 is 0.1 or 1/10 or 10%. So you have a 10% chance of selecting a green ball and then a white ball. Now in this question, if I would have said that first ball that is selected is not replaced, if you did not put that first ball that you selected back in, then the probability of selecting a white ball would not have been 5 out of 10. It would have been a little bit different. It actually would have been 5 out of 9. And again, that would have been conditional on the fact that you did not replace that first green ball. But in this case, we did replace the original ball after we selected it. And so that gave us independent events. And so that's why the notation is set up the way that you see it here. But again, going back to what we saw before, whether you have independent events or dependent events, it doesn't matter what your notation looks like. The theme is still the same. To find the probability of a sequence of events, you take the product of the probabilities. All right, let's take a look at a couple more here. Example C, what is the probability that 2 classmates selected at random are both born in August? So as a sequence of events, think of this as we're finding the probability that the first classmate selected is born in August, and then the probability that the second classmate that's selected is also born in August. So we can see that the probability that the second classmate being born in August is completely independent of the probability that the first classmate is born in August. So once again, we have independent events. We see that the probability of, or we know that the probability of A then B when it comes to independent events is equal to the product of the probabilities. So let's just find the probability that the first classmate was born in August, and that's just going to be 1/12, and then we multiply that by the probability that the second classmate is born in August, and that's also going to be 1/12. And 1/12 times 1/12 gives you 1/144, and 1 divided by 144 as a decimal is equal to 0.0069, and that's if you're going to 4 decimal places, 0.0069. So not even a 1% chance of picking 2 classmates at random and them both being born in August. Okay, last example. An office has 3 smoke detectors. In case of fire, each detector has probability of 0.9 of detecting the fire. if a fire occurs, what is the probability that at least one detector detects it? Okay, so here is a tricky question because we see it involves this at least one concept that we actually saw once before. And we're going to have to apply that also in the context of either independent or dependent events. Okay, so I think the number one thing we should do here is recognize this, that if we're finding the probability that at least one of these three smoke detectors detects the fire, then we're determining the probability that exactly one smoke detector detects it, exactly two, or exactly three, and that can be a really tricky problem to figure out. And so the number one thing to do to start this question is to use the idea of the complement and to say the probability of at least one detecting is equal to 1 minus the probability that none detect. And this is a much easier way to frame this question, because instead of figuring out the probability that exactly one and exactly two and exactly or all three detect the fire, we just have to figure out the probability that none of them detect the fire. Now we can figure out the probability that none of them detect the fire because this is a sequence of events. The probability that none detect the fire is the exact same as saying the probability the first doesn't detect, and then the second doesn't detect, and then the third doesn't detect. So we saw throughout the last couple of videos now that the probability of a sequence of events is equivalent to the product of the probabilities for the individual events. So if none of them are detecting, then the probability that the first doesn't detect, and then the second doesn't detect, and then the third doesn't detect is going to be the product of those three probabilities. So what is the probability that each one does not detect? Well, since each one has a probability of 0.9 of detecting the fire, then each one has a probability of 0.1 of not detecting. Okay, but that's each smoke detector. We need to figure out here the probability that none of the smoke detectors detect. And so that's going to be the probability that the first doesn't detect. I'm just going to write this out just so it's clear. The first doesn't detect, and then the second doesn't, and then the third doesn't. And as we've just said, the probability that any individual detector does not detect the fire is 0.1. And the probability of this sequence of events is therefore going to be 0.1 multiplied by 0.1 multiplied by 0.1. That's applying the formula and the concept that we've been seeing here. And so this is 1 minus 0.1 cubed. And if you do 1 minus 0.1 cubed, this will make you feel a little bit better about these smoke detectors. You end up with a 0.999 or a 99.9% chance that at least one of the smoke detectors detects the fire. All right, the very last video that I'm going to go through is just a review of a lot of the major concepts from throughout this entire module. So I suggest taking a look at that one, and then you'll be able to tackle your homework. Thanks.